Number 74. Experiments were conducted to study the rate of the reaction represented by this equation, which is 2NO gas plus 2H2 gas yields N2 gas plus 2H2O gas. And then initial concentrations and rates of reactions were given here. I love a table. We can get a lot of information from a table, especially if we are in the kinetics world of chem. And brace yourself, it's going to be one rocky road. A through E coming up. I figured I'd do it all in one video for this one because there's a lot of different concepts that, is answered in this question. So basically, if you could do this question, right, and you could do all parts and you understand how each part is done, I think you got this chapter, all right? But let's get into it. So it says, consider the following questions. I'll consider them. So letter A, it says, determine the order of each of the reactants NO and H2 from the data given and show your reasoning. So a lot of stuff going on. So I'm going to start this one by writing up here for letter A. Now in this case for letter A, we need to find the orders of the reactants. And the reactants are NO and H2. Now whenever they give you a chart, right, we cannot assume that this equation that they gave us is an elementary reaction or an elementary step. There might be multiple steps hidden in this overall equation. And by finding the orders, we have to use the chart. Now, we've done tons of problems already using charts, figuring out how to use them, right? So if you do need more of a refresher, we can always go back to that, but I'll be pretty thorough for this one. Now, whenever they're asking for the order, right, and they give you a chart, maybe I'll put this up here. What they're secretly asking you for is, what is the rate law? Because the rate law will give you those orders. Well, the first thing is, what is the general formula of a rate law? It is this right here. And maybe I'll shrink this down a little bit because there's a lot going on. And maybe I could put it over here. Now, for any kinetics equation, right, a rate equals K times the concentration of the reactants raised to those orders. That's what we want to solve for. We want to solve for those exponents. Now, we can't just assume that we're going to take them as the coefficients because we said that we can't assume that this is just one step. Could be multiple steps crunched together. That's why we got to use the chart. Now, in this case, what we're going to do is we're going to write the general rate law that we can write now. So in this case, we have a rate, right? A rate will equal a K value, the rate constant. Now we do have the two reactants, right? We have the NO, so this would be concentration of the two brackets. And when you have multiple reactants, they are always multiplied by each other. So it's the NO times the H2. Now the question is, I don't know what those orders are. So I'm going to label it 1 as X. And since they are independent of each other, right, they have nothing to do with one another, I can't label this as X as well, because then that means that these are the two of the same numbers. So I have to use a different letter. So I like to use X and Y. You could use AB, BU, right, BC, I don't know, right, whatever you want to use. But now the question here is, right, we have two different variables. This is not a calculus course, so we only want to work with one variable at a time. That's when we're going to use a chart to get rid of one of these variables. Now, we just got to work in sections, right? Pick a reaction that you want to work with first. Let's say that we want to find out the order for NO, right? If I want to find out NO, that means that I want to find out what that X is. So if I want to find out for that one, we need to cancel out the other one. You need to cancel out the Y, and the Y is specifically linked with the H2. So what we're going to do is we go to the chart to pick out two trials that have H2 as the same. You want to pick the two trials where H2 is the same. So here's the column that has H2 as the same. Well, here's the column that has H2 in it. I got 4 trials to pick from. I like to call them trials. They're called experiments here. It doesn't really matter. But can you pick the two trials in which H2 is the same? Yeah. Felt like Blue's Clues right there, right? Do you see the mailbox? Or is that Dora the Explorer? I think both of them do it. But can you pick the two trials which are the same? Yeah, right? Trial 3 and 4. So maybe what I'll do is I'll just highlight this, right? But now the question is, well, what are we going to do with these two trials, right? What are we going to do with trial 3 and 4? Well, we're going to put them into the rate law. But let's make it easy for ourselves. What I like to do is I always like to put the higher rate and divide it by the lower rate. Just works out for math purposes better. So go to your rate column. You have these two rates, right? And which one is higher, which one is lower? Well, seems like this one is the higher one. So I'll do trial, or we'll say experiment, 4 divided by experiment 3. And what we're doing is we're basically doing the rate law for 4. So this formula for 4 divided by that formula again for 3. You're just making a ratio. So let's do it. And then maybe I'll highlight these because these have to come along. So let's follow the template. This is our template. And we're going to do experiment 4 over experiment 3. So experiment 4 says the rate is 1.2 times 10 to the negative 4th equals, now we don't have a k value just yet, right? None of these has anything to do with the k, which is the rate constant, so I'll just leave it like that. And then you have your two pieces of information. You have NO, which is 0.002, and then 0.006. And this one is raised to the x, and this one is raised to the y. We're going to take all of that and divide it by the experiment 3 rate law values. So now I have 0.30 times 10 to the negative 4th equals the k value, those two numbers. So we have 0.001 and then 0.006, x and y. Now at this stage of the game, it looks a little hairy, but we can cancel things out. The whole main purpose of this was to cancel out the y's. And since these are basically identical, right? 0.06 divided by 0.06 all raised to the y, goodbye. This doesn't exist anymore. But what else can we cancel out? Yeah, you can cancel out k divided by k. It doesn't matter that we don't know it, right? A k value divided by itself is going to cancel out. So goodbye. And now we basically have two things that we just have to work with. We just have to work with this and this. And this is where we will do the division. So calci time, 1.2 times 10 to the negative 4th divided by 0.3 to the negative 4th. You know, you could plug it in. You could do mental math as well if you want. But this will just equal 4. It's a beautiful, beautiful whole number. So we'll say 4 equals 0.002 divided by 0.001. These cancel out, right? So it'd just be 2 divided by 1. Or you can plug it in, which is 2. And then 2 all raised to the x. That variable has to stay there. So now we can solve for x, right? 2 to the what will get me 4. How many times do I have to multiply 2 to get to 4? Yeah, 2 times. So x equals 2. Okay, so we found out 50% of the question. So determine the order for each of the reactants. So this one is for NO. So NO, and maybe we'll clean this up once we're done here. But NO, or maybe we'll just say NO's order is 2. Now we have to do the same thing, right? But now we want to solve for the y. So we basically start all the way back to square one. So instead, if we want to find out the H2, right, especially we want to find out that y value, we want to cancel out who? Yeah, you got it. We got to cancel out the other one. So now I'm looking for two trials that NO is not, is the same. So what I'm going to do is I'm going to get rid of, actually, maybe I'll keep the blues, but we'll see. Now I go to the NO column and I say, here are my 4 total experiments or 4 total trials. I want to get rid of NO. So which 2 trials is NO the same? Yeah, it's these 2 now, right? 0.006, 0.006. So I'm going to use experiment 1 and 2. And then always do higher rate over the lower rate. So I just look at these numbers just to kind of guide me as to which one's going on top, which one's going on the bottom. Just makes the math easier. This one looks like a bigger number. So we're going to do 2 over 1. So let's write that out. So we're going to do experiment 2 over 1. I love how I'm not even finished with number 1 and I'm running out of room already, but we'll clean it up at the end. But yeah. So let's go for it, right? Experiment 2, and this is coming along for the ride. It's gotta. Let's plug everything in. Experiment 2, 3.6 times 10 to the negative 4th. Keep in mind that I'm still just abiding by my rate law, right? This equals K. Times the concentration of the 2 values. So for experiment 2, it's 0.006 and then 0.002. This one is raised to the x and this one is raised to the y. All divided by experiment 1. So 1.8 times 10 to the negative 4th equals the rate constant. We still have no idea what it is, but that's okay. Times the 2 concentrations. And what do we got? This is experiment 1. So we have 0.006 again, and then 0.001. Now, just note, guys, that as you get better with this, the speed of this question will, the rate in which you'll be able to answer this question will become faster. But I'm just laying it all out for you guys just so that we can follow it step by step. But the same thing goes, right? K divided by K. Even though we don't know the number, doesn't matter. We get rid of it. Goodbye. And now, since these are the same, they go. Bye-bye. So the only things that we're really working with is the rates again, and now the y's. So 3.6 times 10 to the negative 4th divided by 1.8 times 10 to the negative 4th. You get 2 in this case. So 2 equals, we did this math already, right? This was 2. And that's now raised to the y. So I say 2 to the what will get me 2. You are absolutely correct. The y equals 1. Ooh, I don't like that color clash. There we go. So the H2, which was the y, H2's order is 1. So let's just put that over here. So we have NO's order was 2 and H2's order was 1. And that is the answer for A, basically. They say determine the order for each of the reactants, 2 and 1, from the data and show your reasoning. Show your reasoning would be literally all the math that we just did. So I'm going to box this answer off, because this is the absolute answer that we need. And I'm going to put that up here. I'm just going to rearrange some stuff, but I need to get rid of some of this because we got more math to go. So pause the video if you need to, and let me erase, okay? So here we go. Just got to say bye-bye to all of this just because we got more math coming. Bye-bye. So this is going. The only thing that I'm going to keep is the general rate law up there. Uh-oh. That's going to erase the whole thing, right? We don't want that. So we'll just cancel this out. We'll just give us some room. There we go. And let's see now. There we go. Okay. So I'm just going to bring this down. Okay. So now, letter A, all done. Letter B, what is the overall rate law for this reaction? Well, this one will be quick because we have now the generalized rate law. We found out the orders. So all we have to do is just plug in the orders that what we said, right? And we said that NO was second order. So I'm going to just raise the NO to the number 2. So that is a 2 up there. And then H2 is raised to the first. So you can put a 1 up top here, but you don't have to if you don't want to. And that's the answer for B. How quick was that, right? So A was a lot of math. B was an easy one, mainly because we already did most of the work. And that's the answer for the second part. So let's just box that off. We'll probably use that for later questions. And B's done already. C. Calculate the value of the rate constant for the reaction, and then we have to include the units. Okay. So we'll say letter C. We want to calculate K. Now, we could only do this if we had the rate law. So we did have to do A, we did have to do B to get to C. Now, the question here is, we want to solve for K, okay, but we have 4 trials. Now, there's, a lot of ways to find out K, but majority of the time is what teachers or professors just want you to do is just use one experiment, plug it in, and solve. Now, most of the time, I don't know why, they always choose the last value. But, I mean, if it's a rate constant, technically all the experiments should come out to a very, very, very similar K value. So if you want, you can try out one experiment, and I'm going to do another one, and see if we get, a K value that's very close to each other. So I will do experiment 4. So what I'm going to do is I'm going to use experiments 4 values. And what I'll do, just to not get confused, we don't need this anymore. That was for A. And now I'm just going to focus in on number 4's values and see what's going on. I'm going to use the rate law, plug in all the values for experiment 4, and solve for K. So rate equals 1, so 1.2 times 10 to the negative 4th equals K times the concentration of the 2 reactants. So it was NO, which is 0.002, and then 0.006. The 0.02 was raised to the second, and this is raised to the first. So now we just have to, do the math. Now, you can square this first to get that as one number and then times it by 0.006, but you could also take this and times it all by itself. Calci will understand what you're doing. So that's what I'm going to do. I'm going to say 0.002. I'm going to square that. And then once that's done, I'm going to times that by 0.006. You could have done this in 2 steps, but you'll get the same answer. So we got 1.2 times 10 to the negative 4th equals 2.4 times 10 to the negative 8th, and now that is all being times by K. So just solve for K. All I got to do is just divide by that number, right? 2.4 times 10 to the negative 8th, 2.4 times 10 to the negative 8th. Get rid of that. Goodbye. And let's see, we got 1.2 times 10 to the negative 4th divided by 2.4 times 10 to the negative 8th. There we go. So my answer is 5,000, which equals K. Now, they do say include units. So 5,000 what? Bananas? Now, the K value, the rate constant, the units of K, it's not one standard unit, right? The units of K really goes with the overall order. So we need to find out what that overall order of the reaction is. And the overall order is you just got to add up all the orders. So back in letter A, where we said that the order for NO was 2 and the order for H2 was 1, we got to just add them up. 2 plus 1 is 3. Now, depending on what that overall order is, that's the units of K. So there's a K unit for 0 order, there's a K unit for 1, 2, and 3. Now, for a third order, the K units, and maybe what I'll do is we'll just bring this out a little bit. The K units are going to be 1 over molarity squared times seconds. Now, what you can also do if you're in a bind, what you can do is you can use your rate law and plug in the units and solve. You would get the same answer. But now this can be represented as many different things. So we could say, maybe I'll just say 1 over molarity squared times seconds is the same thing as molarity to the negative 2 times seconds to the negative 1. This is the same thing as saying liters squared over mole squared seconds to the minus 1. This is the same thing as saying liters squared moles to the negative 2 seconds to the minus 1. It really doesn't matter which unit you use. You just got to use one of them. They're all the same. So generally, you know, they've been using mole liter minus 1, mole liter minus 1, mole liter minus 1. Oh, and this one, good catch, Christina, right? This one is in minutes. Generally, the unit for K value is over seconds, but that's the unit of time. So good catch on that. Did anybody catch that? Right? Was anybody screaming at their computer or their iPhone or whatever they're using? I heard you. I heard you. So this should be molarity squared per minute. So just, you know, you could use seconds if the data was given in seconds, but if it is in minutes, you got to change all those seconds into minutes. So maybe what I'll say is probably, just to kind of link everything up, we'll say that it's the liter squared mole negative 2 min. Okay, and then that would be the final answer for C. Okay, so C is done. Let's see where we're at here. Okay, D. For experiment number 2, calculate the concentration of NO remaining when exactly 1/2 of the original amount of H2 has been consumed. Okay, so for now this one, they did state that 1/2 of the original amount of H2 has been consumed. Okay, so we got to go to experiment 2. So let's erase these just to not confuse us, because we're not going to use experiment 4 anymore. We're going to use the amounts for experiment 2. Now, they did state that 1/2 of the original amount of H2 was consumed. Okay, so the H2 in experiment 2, the initial amount was 0.002. So let's start with that, and maybe I'll put letter D over here. I think we got enough room. Maybe what I'll do is I'll just move this a little bit over, a tad bit over. Okay. So now, for letter D, right, we know that we're starting off with 0.0020, right, moles over liters times minutes, right? Now, we can simplify this to just moles, right? They didn't necessarily state how many liters we're working with here, right? They gave us no indication as to how many liters we're working with. So we can assume that we are in a 1 liter solution. And if we are timesing it by 1 liter, because we're assuming that's how much how much our volume is, the liters go bye-bye. And then we could do the same thing for minutes, right? They didn't specify how long this was going to take. So maybe, it took 1 minute. So if you times it by 1 minute, the minutes go bye-bye. So we can simplify this junk of a unit here and just say that, hey, we're going to start off with 0.002 moles of the H2. This was initial. Now they're saying that 1/2 has been consumed. So this is initially what I started with. At the end, 1/2 has to be consumed, which means that 1/2 has to be gone, right? Vanished, poof, it made into the product. So it would just be 0.0010, right? Moles of the H2. Okay, so that's how much was consumed. Now, well, let's figure out how much would be consumed of the NO. Now, it seems like this, unfortunately, got to go bye-bye because it's now coming into letter D. But if you want to pause the video, just write that out. That's fine with me, but bye-bye. Now it's all better. But now, according to the balanced equation, because now we're dealing with stoichiometry, right? We're dealing with just moles here. According to the stoichiometry, you have 2 moles, well, 2 NO plus 2 H2. And this will yield N2 plus 2 H2O. But if we just stated that we know that 0.001 moles was consumed, or, that was what was gone, how many moles of NO should also be consumed or gone, right? And this is just a stoichiometry, right? But look at those coefficients. It's a 2-to-2 relationship between the two reactants, which basically is a 1-to-1, right? They're the same number. So if you have, in reality, 0.001 moles, and they should be the same, that means that you would have 0.001 moles of NO that was consumed because they're going at the same rate. So in this case, right, we have 0.0010 moles of NO also being consumed. And because of that, how much did we initially start off with? Oh, we started off with 0.006 moles of NO. We want to find out how much NO is remaining. If the 0.001 NO is consumed and we start off with 0.0060 moles of NO initially, how much is going to be remaining? What would we have to do with these two values? Yeah, you got it. We would have to subtract them. So if we initially had 0.006, we know that we're getting rid of 0.001 because of the ratio. We are left with 0.005, you could add the 0 there, moles of NO remaining. And that is the answer for D. So this one was kind of just going back to stoichiometry. Wow. They're going all over the place for this question. That one was fun. So D is done. And just for, just to put the units correctly, they wanted to calculate the concentration of NO remaining. We just did moles, but you could just assume that we have the liters back in the 1 liter solution. So we can say that 0.005 molarity of NO is remaining because specifically they're asking for calculate the concentration, and concentration is always a molarity. So we did the math for moles because generally when you are doing stoichiometry, you should always do it in just moles. Get that value, and then if there was a different liter, you would have had to have divided it, but since we assumed that it was 1 liter, 0.005 divided by 1 is the same as molarity. So there you go. And now for letter E. The following sequence of elementary steps is a proposed mechanism for the reaction. So we have 3 steps here. Okay? And now it says, based on the data presented and everything that we have done, which of these is the rate determining step? Show that the mechanism is consistent with the observed rate law for the reaction and the overall stoichiometry of the reaction. Okay. So for this one also, I do need a little bit of room. So what I'm going to do is I'm going to just manipulate some of the information that we already put down. So if we need to get rid of if you need to write down anything, just pause the video again, just so that I can, erase. But I will be erasing the work for K, because that's just taking up a little bit too much space. So goodbye for that. This, it doesn't really, let's see. We could pull this up. Maybe hide that little dot there. That's killing me. Oh boy. That little dot. Shouldn't have been in there. Okay, so that's going to give me some room for that. Let's see. For letter D, I guess we'll move letter D up here. And at the end of the day, this is basically what we came up with. So if you do need the math, pause the video. I'm just going to erase this, okay? Just because I do need a little bit more room for E. And once I erase this, we can start. Okay. So in this case, now we have to look at the proposed mechanism. Now there's 3 steps, right? And we want to find out which one is the rate determining step. So the first thing is always know the general rule. If step number 1, right? If step number 1 looks just like the rate law, if it's identical, then that means that is the slow step. So that's always the first thing that I'm going to do. I can always decide if the first step is the slow step. Now, the first step in the mechanism, right, is NO plus NO. Now, if we wrote a rate law for step number 1 using the same general formula, but now since these are all elementary steps, the orders are the coefficients, because now we know that this is one independent step, this is another independent step. So you can take those coefficients as the orders. So step 1 rate law would have been rate equals NO, because those are your 2 reactants, but you have 2 of them. So this would have been NO squared. Now I say to myself, does this match the rate law that we have? Well, it's got the NO squareds here, but oopsie, we have no H2. So I know that since this is an exact not match, I know that step 1 is not the slow step. So I limited down to 2 of the steps. Either step 2 or step 3 is going to be the rate determining step. And the rate determining step just means that is the slow step. Okay. So I eliminated it down. Now I'm down to 2 or 3. So we just keep going, right? Let's see. Is step 2 going to be the slow step? Well, we will write down the general rate law. So the rate law we'll say is rate equals K times the concentration of those reactants, N2O2 times H2. And since we have an elementary step, we can use those coefficients. So this would be raised to the first and this would be raised to the first. Now I say to myself, does this match this? Well, not at the moment. But now there's another little thing to talk about here, is that if you have intermediates in the rate law, you need to cancel them out. So in this case, right, we didn't have to really discuss any intermediates with step number 1 because NO was a reactant in my overall equation. But now I see that I have this N2O2. And if I look at my general equation, N2O2 is not there anymore. It vanished, right? And N2O2 isn't even on here. So N2O2 has to be an intermediate. So we'll say that. So we're still on the hunt because this could potentially be the rate law. It just depends. Now we just need to cancel it out. Well, which step also has N2 in it? Yeah, step 1. Step 1 has N2O2 in it, right? So what we're going to do is we're basically just going to substitute in the N2O2 for what it really equals, right? The rate law for step 1, if we're going to say that this is now a fast step, generally speaking now, if you're doing, multiple steps, like if step 2 is the rate determining step, step 3 is the rate determining step, the ones before it is going to happen in a fast manner. Which means that you have a forward and a reverse reaction going on. So maybe we'll say over here, step number 1, that the rate of the forward will equal, so we'll say rate of the forward equals the rate of the reverse, because this is happening in a fast equilibrium. So now you basically have 2 rate laws, right? The first one, the forward one, would equal the one that we had before, right? And this obviously has to equal K, right? K times NO squared. And the same thing here, it would be K of the forward reaction times NO squared, which equals the rate in the reverse. If you're doing it in the reverse, that means that this is now your starting amount. So that would equal K reverse N2O2. And now I have a formula that can go in replace, of N2O2. If I just, divided by both sides by KR, right? Divided by KR. Sorry that I'm, going down all the way to the bottom of the screen. But now, and maybe we'll just cancel that out, right? So now if I just plug this in for this into my step 2, I have rate equals a K value times by now all of the N2O2 from step number 1. So this would be a KF over a KR, but now it's times by NO squared. And then keep going, times by H2. Now all of these 3 K values, right? The K times the K forward times the K reverse, they're all just going to be multiplied and turned into one big K value. So this, for our simplicity purposes, we can just say that, hey, this will all just get canceled out into just one big K value. And because of that, maybe I could just get rid of this parenthesis right here. And now let's see if it matches. Rate equals some K value times NO squared times H2. There it is. It's identical. So whichever one matches identically, that's going to be the slow step. So we know that step 2 is the slow step, or the rate determining step. So which one is the rate determining? The second step. Step 2. And now it said, show that the mechanism is consistent with the above rate law and the overall stoichiometry of the reaction. Basically, all that you have done here will suffice for, the work that you need to do. And oh my goodness, we are done with this question. But like I said in the beginning, it was going to be a rocky road. Thank you for, staying all the way to the end. You guys are the real, the real supporters, but thank you. But there was something else that I wanted to say. Yeah, so as I said in the beginning, if you could do this problem and flow with me, making sure that, oh yeah, I know how to do A, I know how to do B, all the way up to E, you got this. All right? So super, super proud of you. Thank you for joining me for the ride. You guys are truly amazing. I really do appreciate all you guys. Thank you so much, and thanks for supporting the channel. We just want to, get these videos out there for you guys just to help you in your classes. So thank you so much, and I will be talking to you soon, okay? Have a great day, and I'll talk to you then. Bye-bye.